Hi everyone, this is Dr. Saida Falafini from Cal Poly Pomona. So in this session, we're going to continue on the queuing theory. The system that we want to talk about today is this system. Can you tell me what is it? What does this system mean?
The first M is inter-arrivals are independent.
And what does M mean?
They're independent of each other and exponentially distributed.
And the inter-arrival times are exponentially distributed. How about this second one?
Service times are exponential.
Service times are exponentially distributed. Next.
There's only one server.
One server. Next. Queuing discipline is general.
Yeah, general queue discipline. Sorry, I was on mute when I was responding.
No worries. Next.
Size of the queue, or like the capacity.
Capacity of the system is infinity. We can have as many people as enter the system. And next.
Size of population.
Size of the population is infinity. Like there's no limit on how many people can come from this population to the system. So this is basically the structure of one of the basic general queuing systems that we may face. And we want to start with this system, and gradually as we go to other systems, we are changing these parameters and making the system more complex. So what we want to calculate basically for these, for any one of these queuing systems that we are looking at are a couple of things. Where first, we want to calculate pi j's. Can you tell me what are pi j's?
The probability that in the long run there is j people in the system.
That's what pi j means, the probability that there are j people in the system. And so we want to calculate pi j for any one of the queuing systems. And the other thing that we want to calculate, remember we talked about number of people in the system, in the queue.
Isn't that L?
That's LQ. Number of people in the system, that one is L. Time waiting in the queue
Is TQ.
W Q, and then time waiting in the system W. We can also correspondingly calculate number of people in the service area. We call it LS, and time spent in the service area, and I'm going to call it WS. So basically, if we calculate L, LQ, W, WQ, we can calculate LS and WS easily. So usually the top four are the ones that are, we extract the formula for the top four, and then the other two are calculated automatically. I will show you. So for any queuing systems, we want to find the steady state probabilities, LLQ, WWQ, LSWS. Okay. So, and that's basically what we are going to focus on for the rest of the semester. We go through different queuing systems, and for each one of them, we extract these values. And we are going to start with M1, GD, infinity system, which is probably the most basic, simple type of queuing systems that we may have. So basically here, there is one server. So there is one server. This is the server. And then there is one queue. People come, wait in the queue. They go get the service on the server, and then they leave the system. So basically, that's the simple structure of this queuing system. As you are going to take note for the rest of the class, what I want you guys to do, which is going to help you in the exam if you want to prepare some cheat sheet later for the exam and get ready. as we are going to talk about any system, make sure to write the type of the system like bold on top of as the heading of the section. Then we go through a bunch of formula examples and everything, and those are all for this system. And then we go to the next system. Okay, that's maybe MMS, GD, blah blah. So that's another type of system. So again, give it a bold heading with the type of system that we're going to talk about, and then a bunch of formula and examples related to that. That way, when you want to prepare your cheat sheet, again, I recommend that you write this as the type of queuing system for which you are writing the formula, so that you know the formula is for this type of system. Because in the exam or in the homework, I give you the problem statement, but I don't tell you what type of queuing system we are looking at. So when you read the problem statement, you have to decide, oh, that problem statement matches, for example, this definition or that definition. Then you can go back to your cheat sheet and look at the formulas under this type of queuing systems and see what I'm asking from you and what formula you have to use. I have seen a lot of time in the exam that people write, I know this is this type of system, but I don't know why I don't have the right formula in my cheat sheet. So I think if you take note this way and if you prepare your cheat sheet this way, then you won't get confused in the exam as, oh, I need this formula for this type of system, but I don't have it, and blah, blah. So that's what I strongly recommend. Okay, so we are going to talk about this type of system. So the first thing I want to do is to extract the steady state probabilities. So first, tell me, so, and everyone knows this, the state of the system is what? So what is the state variable here? So the state itself is having J number of people in the system, right? So basically the state variable is number of people in the system. And then the probability of having J number of people in the system, that's pi J. So tell me, what are the possible values for the number of people in the system?
0, 1, 2, 3, ... infinity.
Yeah. In this system, we assume that the rate of arrival does not depend on how many people are in the system. Because in the very general rate diagram that we developed for a general queuing system we talked about in previous session, if you remember, we had lambda 0, lambda 1, lambda 2, which means the rate of arrival depends on the state of the system. If there is one person in the system, if there's two people in the system, and so forth. But here we assume the rate of arrival does not depend on how many people are in the system. So no matter if there is 0 people in the system or 1 person or 2 people and so forth, the rate of arrival to the system is lambda. So that's the assumption that we make for this system. So basically, no matter how many people are in the bank, always on average, for example, 10 customers per hour arrives to the bank. That's basically what it means as an example. The other assumptions that we are going to make is that the rate of service or the rate of departure does not depend on how many customers or how many people are in the system, or how many entities, how many people or entities are in the system. And again, in the very general scenario that we talked about in previous session, we had mu0, mu1, mu2, meaning that what is the rate of the departure or rate of the service when there is one person in the system and there are two people in the system and so forth. But here we assume the rate of the departure or the rate of the service does not depend on how many people are in the system. So no matter what, the rate of the no matter how many people are in the system, the rate of the departure is mu. So again, for example, in a bank, no matter how many people are in the system, it takes an agent on average. An agent can provide service to on average 5 customers per hour. Okay, so that's basically what it means. And this rate of people that an agent can provide service to in an hour is not going to change no matter how many people are in the bank waiting or so forth. Okay, So then this becomes basically our rate diagram for this system. Do you remember what was the formula for pi j when we calculated the steady state properties for a general system? We said pi j equals to pi 0 Cj, right? And then Cj was now. And in this system, in the case of this queuing system, when that lambdas and mu's do not depend on how many people are in the system, then this formula becomes what? Lambda j becomes pi 0 multiplied by Cj. And Cj, if I put lambda instead of all these possible lambdas in the numerator, if I just put lambda here in the numerator, so that's going to be j lambda, right? So that's going to be lambda to the power of j over, and then in the numerator also, if instead of all these mu1 to all the way to mu j, if I put just mu, then it's going to be also mu j in the denominator as well. So then this becomes basically lambda over mu to the power of j pi 0. So for then pi 1, this thing is lambda over mu pi 0. For pi 2, this becomes lambda over mu to the power of 2 pi 0. For pi 3, then this is lambda over mu to the power of 3 pi 0, and so forth, right? And let's consider, let's give a name to lambda over mu. So I'm going to show lambda over mu by rho. And just consider this later. I will get back to this and I'll explain really what it means. Just as a notation, I'm going to show lambda over mu by rho. I will explain in a little bit what does rho, what rho means, and what is the whole concept of traffic intensity of the queuing system. Okay, so just keep that in mind. So basically, and as I said in previous session, we know there are two things we know about any queuing system to be able to analyze it. We know the rate of arrivals to the system. We know the rate of departure or the rate of the service in any one of the servers. So all these lambdas and all these mu's should be known to us to be able to analyze any queuing system. And similarly here, we know the value of lambda and we know the value of mu to be able to analyze the queuing system. So in these pi j's or all these pi's that we want to calculate, then definitely the lambda over mu section is known, right? That's the data that is given to us. The only part that I need to know is the pi 0 value. If I know the pi 0, and given the fact that I know the lambda over mu part, then I can calculate lambda j for any possible value of j. So I want to see how can I calculate pi 0. Do you remember what we did in previous session to find pi 0? What is the trick or the formula we used?
We make pi 1, pi 2, pi 3 equal to pi 0, and then we make pi 0 plus pi 1 plus pi 2 equal to 1.
Why? Yeah, so not just to pi 3. So this is just goes to all the way to infinity, right? Pi j.
Yes, because all the rows are equal to each other. But Professor, I have just a quick question.
Yeah, go ahead.
Here we're assuming that lambda and the mu are equal for all the possible...
Yeah, so we assume that, as you can see here, we assume that the lambdas, the rate of arrival of customers to the system does not depend on how many people are in the system. Similarly, we assume the rate of the departure or the rate of the service in the system does not depend on how many people are in the system. So all the lambdas and mu's are the same.
Perfect. Yeah, because I remember when solving it, we used like two different lambdas when we were calculating the lambda and the mu. So that's why I just want to make sure about this.
Yeah. So that's why I said assume. So these are the assumptions that we make for this system. The rate of arrivals do not depend on how many customers are in the system. The rate of departures do not depend on how many people are in the system. So those are the assumptions we make about this system. And so this, okay, so and then all the way to pi j, all the way to infinity. What is this sum?
1.
1. Now, pi 0 I know pi1 is rho pi 0, pi2 is rho to the power of 2 pi 0, right? So instead of lambda over mu, I just put rho. And pi3 rho to the power 3 pi 0 all the way to infinity equals to 1. So then what I have is pi 0, 1 plus rho squared all the way to infinity equals to 1. So, and we know the value of rho's, right? So because rho is lambda over mu, and I know lambda and over mu, and I know mu. If I can find the value of this infinite sum, then I can find the value of pi 0, because then pi 0 would be 1 over this infinite sum. And I'm going to put this infinite sum as s. So then pi 0 will be 1 over s, right? So about all I need to do is to find the value of this infinite sum. So let's do that. Let's see how we can find the value of that infinite sum. S equals to, that's what I have from previous slide. I'm going to multiply both sides of this equation by rho. So then I have rho s equals to, then what I'm going to do is to calculate the first equation minus the second equation. So this is what I have on the left, the first equation minus the second equation. What I have on the right, if you see when I say first equation minus second equation, on the right, all the rows and row squares, everything is going to cancel each other. And the only thing that is going to be left is 1. So all the rows, this row, for example, is canceled with this one. This one is canceled with this one. This one is canceled with this one, and so forth. So the only thing that is going to be left is this 1 here. As a result, s 1 minus rho equals to 1. So s equals to 1 over 1 minus rho. So that's basically what I want here. So here I said s equals to 1 over rho, right? That's what we just calculated here. So here s equals to 1 over 1 minus rho. And as a result, when you do the calculations, pi 0 is going to be 1 minus rho. So then basically what I have is pi 0 multiplied by s, and s is 1 minus rho equals to 1. So when you do the calculation, then pi 0 is 1 minus rho. That's the value of pi 0. And rho, again, is lambda over mu. It's known. So then pi 0 is known. And then when I put pi 0 in any one of these equations, I already know the rest of the equation, so I can calculate the probabilities. So basically the probabilities, pi 0 is 1 minus rho. That's what we just calculated. And then pi 1 will be rho multiplied by 1 minus rho. Pi 2 will be rho square multiplied by 1 minus rho, all the way to pi j equals to rho j 1 minus rho. So basically that's the formula for calculating pi j for this system. So make sure, as you are taking note, make sure to write down what does how we calculated pi 0. Make sure to write down how we calculated pi j's general in this system and so forth. So these are some of the formulas you need to know and you will use later. And then one more thing is that, as you can see here, s equals to 1 minus rho, right? So, and just look at here. So basically we said pi 0 multiplied by s equals to 1. So basically pi 0 multiplied by s equals to 1, right? Pi 0 multiplied by 1 over 1 minus rho equals to 1, which basically led to pi 0 being 1 minus rho, right? That's what I wrote here. But here in this formula, in this formula, I do not want rho to be 1. Yeah, if rho equals to 1, then s equals to 1 over 0, which is infinity, and everything is undefined, right? So I definitely do not want rho to, I do not want it to be 1. Also, I do not want rho to be greater than 1, because if rho is greater than 1, then s is a negative, becomes a negative value, and then the pi 0, which is the probability of having 0 people in the system, as 1 over s becomes a negative value, which is wrong because we don't have any probability which is negative, right? So that means I don't want also rho to be greater than 1. So definitely then rho should be less than 1. I don't want it to be 1. I don't want it to be greater than 1. So definitely rho should be less than 1. And I don't want it to be negative as well. So it should be greater than or equal to 0 and less than 1. Okay, so it's important to know this condition, because if rho is not in this condition, that means everything in that queuing system is undefined. So if rho is a number greater than 1, your S is negative, all the probabilities become negative. So that basically nothing is meaningful in that queuing system. If rho is 0, if rho is 1, your S is infinity, the probabilities, all of them are 0. And so none of the things make sense. Also, let me explain here. Remember here I told you rho is the traffic intensity of the queuing system, right? And rho is lambda over mu. When I say rho should be between 0 and 1, what does that mean? Rho should be less than 1. That implies that lambda should be less than mu, right? So if rho, which is lambda over mu, should be between 0 and 1, that's what we just wrote here. Rho less than 1 means lambda should be less than mu. And that's basically the condition for this queuing system to be meaningful, for these probabilities to exist and make sense. So tell me, what does this mean? Lambda less than mu. The arrival rate to the system should be less than the departure rate from the system. And what does that mean? If you have, for example, a barber shop, for example, a simple barber shop, and there's only one barber in this barber shop. And if the rate of arrival, let's say you get 20 customers per hour, if the rate of arrival is greater than the rate of the departure, you get 20 customers per hour, but the barber can do the haircut for 10 customers per hour. What happens in this barber shop over time? If you just let this system to continue working, what happens in this system? 20 customers per hour come and only 10 customers per hour can leave. Over time, we just get more and more and more and more customers accumulated in the system. So at some point, basically the number of people in the system, pi j, is going to explode. So this queuing system is not stable. So that if the rate of arrival to the system is more than the rate of the departure in the system, then the number of customers that come to the system is then the number of customers that are in the system is just going to increase and go all the way to infinity, and the system is going to explode. So that's not a valid queuing system at all. So that's basically what this whole condition here means, that the rate of arrival to a queuing system should be less than the rate of the departure from that queuing system, for that queuing system to be valid so that we can analyze it. And that's basically why this whole rho less than 1 means. And we call it traffic intensity because it just shows the level of traffic in the system. It's the rate of arrival divided by the rate of departure. It gives you a sense of the traffic in the system. That's why it's called traffic intensity of the queuing system. Let's go and calculate L. What was the definition of L? One more time. L is number of people in the system. What are the possible value for number of people in the system? We just draw a rate diagram. What are those possible values? 0, 1, 2, all the way to infinity. If I want to calculate L, which is average number of people in the system, how should I calculate the average? Like any random variable, we know the possible values. If I want to calculate the average, I multiply each one of these values by the corresponding probability and then add them together. Pi 1 is going to be multiplied by pi 1, 2 is going to be multiplied by 2, 3 is going to be multiplied by pi 3, and so forth, right? So then L is going to be, I'm going to write it just as a sigma j, which is number of people in the system, multiplied by pi j, which is exactly what I wrote here with the green. J number of people in the system multiplied by pi j, 0 multiplied by pi 0, 1 multiplied by pi 1, 2 multiplied by pi 2, and add them up, j from 0 to infinity. So that gives me the average number of people in the system. And we know we calculated pi j is rho j 1 minus rho, right? We just calculated that. So what pi j is rho j, rho to the power of 1 minus rho. I can bring the 1 minus rho out of the sigma because it doesn't depend on j. So it's 1 minus rho sigma j rho to the power of j from 0 to infinity. So all I need to do right now is to calculate this part. See what is this infinite sum. If I can find the value of this infinite sum, I already know the value of 1 minus rho because rho is lambda over mu, which I know. So I know 1 minus rho. If I can find this infinite sum, then I can find L. Let's see how we can calculate that infinite sum. So I'm going to call this, let's say, Z. If j is 0, obviously that is 0. If j is 1, that is rho. J is 2, j is 3, right? Then I'm going to multiply both sides by rho, similar to what we did for the other one. Then the right side becomes rho square. I'm going to calculate z minus rho z. And then on the right side, I will have rho, and then 2 rho square with this rho square, I only have 1 rho square, 3 rho cube, and then 2 rho cube, I will have 1 left, and the same for the rest of the expressions with this rho, which is not being cancelled with anything. So then this is what I have. So then z in 1 minus rho equals the summation on the right. If you remember, we calculated this summation just a little bit. What was that? Remember here, this summation basically is part of this. We calculated that S, right? Which we said is equals to 1 minus rho. That summation that you saw on the other side is basically this part of this. In the other slide, we said 1 plus rho square is S, which is 1 over 1 minus rho. So then, if I only want this part, which is exactly what I want here, then just this part equals to (1 over 1 minus rho minus 1). Then if you do the calculations, then this part is going to be, do the calculations here, that's what you will see. 1 over 1 minus rho is going to give you this rho over 1 minus rho. So then the summation on the right side of this equation is rho over 1 minus rho. On the left side, we have z 1 minus rho, and as a result, I can calculate z to be rho over 1 minus rho. That is the z I need to put here to find L. 1 minus rho over 1 minus rho square, which is going to be rho over 1 minus rho. So L is rho over 1 minus rho. That's basically the formula for L. If instead of rho, I just replace the lambda and mu, you can also write it as lambda over mu minus lambda. So instead of rho, remember rho is lambda over mu, right? So if I replace lambda over mu instead of rho and do the simplification, this is basically what you have at the end. So make sure to highlight the formula for L because that's the one that you need to use to answer a question. So we calculated L. We also have LQ, right? We want to calculate LQ. What are the possible values for number of people in the queue?
0, 1, 2, 3, and so on.
LQ is average number of people in the queue, right? So I need to calculate average of these numbers. So I have to multiply each one of these numbers by its probability, and then add these multiplications together, and that would give me LQ. However, first tell me this number. This means 0 people in the queue. When do I have 0 people? What is the probability of this? What if there is 1 person in the system? When would that person go?
The server.
To the server. When there is no one in the system, 1 person comes in, the person doesn't stay in the queue, the person goes to the server to get the service, right? So if there's 1 person in the system, then that person definitely goes to the server. How many people are in the queue? 0. So that is another scenario where when there is 0 people in the queue. So pi 0 is trivial. So pi 1 is the scenario when there is 1 person in the system. However, that person is in the server, so the number of people in the queue is 0. How about 1? 1 person is in the queue. When does that happen? What is the probability associated with that? If 1 person is already served, the server is busy, then 1 person who is in the system should wait in the queue to finally get the service. So this is the situation when there is 1 person in the queue. So when does that happen then? So if there is 1 person in the queue, that happens with the probability of pi 2, because pi 2 means 2 people in the system, and only when 2 people are in the system, 1 of them is with the server, 1 of them is in the queue, then I have 1 person in the queue. How about pi 2? When do I have 2 people in the queue? When there's 3 people in the system, 1 of them is in the server, 2 people are waiting in the queue. So I will have 2 people in the queue when I have 3 people in the system, which happens with probability of pi 3. Okay? So I know the possible values and I know the probability of each one of them happening. So if I want to calculate LQ, I simply have to add these possible values by their probabilities and add them up. So that becomes sigma. These pi j's are multiplied by j minus 1, right? Pi 1 is multiplied by 0. 1 minus 1 is 0. Pi 2 is multiplied by 1. 2 minus 1 is 1. Pi 3 is multiplied by 2. 3 minus 1 is 2, and so forth. So then j goes from 1 to infinity. We start from here, multiplying by pi 1, pi 2, pi 3, and so forth. So that's why I said j from 1, starting from pi 1 to infinity, but each one of these pi j's is multiplied by j minus 1. So now I want to calculate. Now I want to find out what is LQ. So I want to do the simplification and find out the final value, similar to what we did for L. If I multiply pi j and put 2 sigmas, so this is going to be j from 1 to infinity, j pi j minus sigma j from 1 to infinity pi j. Tell me, what is this? Didn't we just calculated this? Remember when I wanted to calculate L, the initial formula we had for L was sigma j pi j, j from 0 to infinity. So how this one, this green, is similar to this one. J here, it starts from 0, but it doesn't matter because when j is 0, j pi j is 0. So it doesn't matter, j starts from 1 here and from 0 here, because when j is 0, there is just 0. So then the first expression of this equation is L, which should be just calculated. And then how about the second part? What is this? Which is basically pi 1 plus pi 2 plus pi 3 all the way to infinity. So this is 1 minus pi 0, because the sum, the 1 is when we also add pi 0 here. Pi 0 plus pi 1 plus pi 2 plus all the way to infinity, that's 1. However, if pi 0 is not here, then the sum of the rest is 1 minus pi 0. LQ is L minus 1 minus pi 0. We calculated L to be rho over 1 minus rho, and pi 0 1 minus plus rho. Just because minus pi 0, so I just apply the minus. So then if we do the simplification, LQ becomes rho square over 1 minus rho. If I put lambda over mu instead of rho, when I simplify it, it's just going to be lambda square over mu minus lambda. This formula is important. Write it and put it in a box. That's one thing that you're going to use. So if I ask you, oh, we have a queuing system, and then you realize, oh, this is actually an MM1, and I ask you, what is average number of people waiting in the queue? Then you use this formula to answer my question. You don't need to prove anything. You don't need to do this calculation. I do the calculations and the proofs here for you so that you know how these formulations are extracted, but you don't need to do all these calculations. All you need to know is to know LQ and L so far, and then you're good to answer the questions. That's why I said, make sure to write these formulas, because you know these are the formulas for LQ for MM1 system. When we go to other type of systems, you will see that how these formulas will change. We calculated L, we calculated LQ. What is left? W and WQ. W is the average time in the system, and WQ is average time that these entities or customers wait in the queue. So there is a formula that has been extracted. We are not going to go over the proof or anything. It's called Little's law. And this formula basically says L equals to lambda W, LQ equals to lambda WQ, LS equals to lambda WS, I believe. Okay, so now let's see what does this formula. So basically what does it say is that if you have L, LQ, LS, we know how to calculate L and LQ, and I will tell you in a little bit how to calculate LS. And lambda is also known. That's the rate of arrival of customers to the system that you should know for any queuing system to be able to analyze it. Then you can use this Little's law to calculate W, WQ, WS. So what does this formula mean? So I'm going to just explain this formula intuitively so that you know what it means, but we are not going to extract it or prove it or anything. The only thing you guys have to do is to just make sure to write these formulas and know them, because you're going to use them to answer any questions related to W, WQ, and WS. So what does this formula mean? So let's assume customers come to the system with the rate of lambda. So on average, lambda customers per hour arrive to the system. And let's assume one customer comes right now, and then this customer is going to stay in the system W time unit, right? W is the waiting time in the system, time in time unit or whatever it is. So let's say hour. So W is the number of hours that the customer waits in the system before the customer leaves. And so by the time that the customer leaves, if we assume that lambda people have arrived per hour, the total number of people in the system will be lambda W, which is L. L is the number of people in the system, right? We say that lambda people per hour arrive to the system. In every hour, we get lambda people come to the system. And then every person stays W time unit in the system. So if I just come right now, I'm going to stay in the system W time unit, and every hour, lambda people per hour arrive to the system. So by the time that I leave, lambda multiplied by W people are in the system. Those are the ones that have come to the system. So then L, which is the average number of people in the system, will be L equals to lambda W. So just consider that and trust these formulas to calculate W, WQ, WS. And then remember I told you if you know L and LQ, you can automatically calculate LS. So I don't need to extract the formula for L. That's because if I write L, number of people in the system, it's equal to number of people in the queue plus number of people in the server, right? Similarly for W, the time in the system is the time you spend on the queue plus the time you spend with the server. And if and just that formula also always holds. So if you have calculated L, if you have calculated LQ, then you can calculate LS. If you have calculated W, if you have calculated WQ, you can calculate WS. And when we do the calculations, actually the formula LS is rho, and then WS is 1 over mu. And for WS, it also makes sense. Can you tell me what does WS mean? What is WS? Yeah, so the definition of WS is average time spent in the server, right? That's what WS means. W means average time spent in the system, average time spent in the queue, average time spent in the server. That's basically the service time of that customer, because it's just one server. The person goes to the service to get the service and leaves. So the average time spent in the server is basically the service time of that person. And given that the fact that we know the service rate is mu, the service time is 1 over mu. So if I know mu is 6 people per hour. So let's say this barber shop, this barber, or this server can provide service to 6 people per hour. We said WS is the time spent with server. Or this is, in other words, so this is the time spent with the server or the service time of each customer. So WS equals to 1 over mu, which is 1 over 6. And the unit will be inverse to hour, basically per person. And if I want to write it based on minute, so I would say this is 60 minutes per hour. This hour and this hour cancel each other. 60 divided by 6 is 10. So this is going to be 10 minutes basically for each person. So the WS, which is the time spent with the server, is just 10 minutes, which is calculated based on this formula. So that's why in our formula, when we put the numbers here and here, when we put the numbers here, and we calculated LS and WS, the WS equals to 1 mu makes sense, and that's what we also see. So make sure you know how to calculate L, LQ, LS, WQ, WS.